Now this video is going to go into quite a bit more complex mathematics so that we can show the relationship to the single sideband via the quadrature form. So recall in the previous videos we saw that the single sideband signal could be written in a quadrature form where we used the Hilbert transform. Then we saw the quadrature amplitude modulation signal could also be written as two messages in quadrature. Well, the VSB signal can also be rewritten so that we can understand that it also has a quadrature form, and therefore all of our bandwidth efficient modulations can be seen in quadrature. Now this quadrature meaning is basically could be thought of as orthogonality, or two signals that are 90 degrees out of phase with each other. So we're going to try to come up with a way so that we can write our VSB signal in terms of the message being modulated by the cosine wave and some variation of the message being multiplied by a sine wave. So that's what this video is going to show. So the first step is to define a new transfer function d, and we're going to say that our d transfer function is imaginary and includes this input filter that's been shifted at plus and minus fc. And then we're going to define a new version of the message where we have the message mv is equal to d multiplied by f. And recall, this is very similar to the Hilbert transform that we defined previously, where we said we could have our message that's been Hilbert transformed if we passed it through a transfer function with this form, which again was imaginary. So we've defined a new transfer function, and based on that, we can get a form of the VSB message, which can be written like this. And this VSB message now has real parts and imaginary parts, and some of the components are MV, and some of the components are just the original message M. These MV components, right, are messages that have passed through the filter, right? Or they've passed through this input filter. And so we're going to see that this gives us a quadrature form. So the filtered form looks like this. The quadrature form looks like the line below it. And now we're going to start color coding them into the real terms and the imaginary terms. And we see that in the imaginary terms, we have the F minus FC portions, which I put in green, and then in purple we have the imaginary terms, which are F plus FC. So our filter transfer function is D, and we've defined our new variation of our message MV as D multiplied by M. And so we're going to look at the green form and the purple form, and we're going to look at these in parallel. So for the green form, we're going to have to shift to minus FC, and for the purple, it's plus FC. So first, we have our filter, and for the green one, right, we're going to use this version of the filter because, recall, we said that the filter D was going to have two forms of the filter, one for the minus FC and one for the plus FC. Okay, so we have our green form and our purple form. We pass both of them through the transfer function D. For the minus FC, we're going to pass it through the form of the transfer function where we have the HI at plus FC, and for the purple, it's minus FC. Now, when we do that, right, we're going to have to substitute in for F, right? We're going to have to put in F minus FC into here, and that means it's going to go into here. And we're going to have to put in F plus FC into the transfer function here. So this is going to be F plus FC, right? It's going to go in here, and that means it's also going to go into here. When we do that, right, we have now substituted F, right, is F minus FC and F plus FC into this form. Now, when we simplify this down a bit, right, because we have the minus FC and plus FC and the plus FC and minus FC, that's going to simplify the argument of our filter quite a bit, right? It's going to take it down just to F for both of these. So this is quite a bit more simple. Now we can see that this MV and this MV can be rewritten in terms of the transfer function. So these terms are going to go in here, just like so. Now we have this as our form of the VSB signal. So if we pull this J out, so these J terms, if we pull them out, they're going to come out front now. And we can see now we have some J over J's, so those are going to cancel out. Then we're going to distribute these terms. So we're going to distribute this into the 1 and the 2 HI. So this form is going to get distributed into here and here, and this one is going to get distributed here by the 1 and also into the part that's being multiplied by the filter. Then we're going to distribute the plus 1/2 and minus 1/2 in. So we're going to get rid of that 2 and this 2 by doing that. So this is going to leave us with this form of the VSB signal. Then we can observe that some of these terms are going to cancel. So this term and this term, right, this is a plus term, this is a minus term, those cancel and go away. And then we can also see that there's more terms that we're left with that cancel. So these ones, right, this came down here, this came down here, these ones are also going to cancel with each other. So now we're left with a much more simple VSB signal. And if we simplify this just a bit more by pulling that HI out, we can see we're left with this. And as you recall, right, if you compare this to the original, it is identical. So this means, right, that at first you just had to rely on me telling you that it was true, but we can define some transfer function that looks like this. And if we apply that transfer function and rewrite our VSB signal using it, it turns out, right, these two things are identical. And now we just went through that long derivation, which was a bit annoying, but recall our original goal was to compare this in the quadrature form. So if we want to compare this in the quadrature form, we can see that these two are identical expressions when we've defined that special transfer function d, which gives us a mv term. And this means that we can define this mv, and we can define this as the so-called vestigial transform, which gives us a time domain version of this, which is the message plus a vestigial transformed message multiplied by a sine wave. And this sine wave is 90 degrees, right? It's 90 degrees out of phase with the cosine wave, which we can say is quadrature. And so comparing this, right, the VSB and the SSB, their quadrature forms look very similar. It's our typical modulated message plus some quadrature form, right? So some form that is 90 degrees shifted. And comparing all three of the amplitude efficient modulations that we've discussed, we can see that they all have very similar quadrature forms. So hopefully this is a bit of a payoff for all of the long discussions on Hilbert transforms, looking at some of these detailed math, complex numbers. But basically, all three of these can be seen as quadrature forms of the message. So the original message on this side, and then this side is in quadrature, right? The sine wave is a 90 degrees phase difference. And this MV, the vestigial transform, right? This was a kind of quadrature transform that has shifted. This Hilbert transform was also a quadrature transform. And then we can see our other message. We could also just take a completely different message and multiply it by the quadrature of our original carrier frequency. So comparing all three, we can see that our VSB signal can also be written in quadrature, just as we saw the other two forms written as.